Hi everyone, this is Jiang. Today I will talk about a fast graph update library for FPGA-based dynamic graph processing called GraSU, which copyrights from Huazhong University of Science and Technology. Before talking to what GraSU is, I would like to show that the graph processing is ubiquitous in our daily life, like social network analysis, information tracking, recommendation systems, and knowledge mining, and so on. In recent years, FPGA accelerations has been demonstrated to effectively boost the performance of graph processing. In particular, FPGA can be regarded as one of the most promising hardware platform of graph processing due to its parallel low power consumptions and fixable configurability. Unfortunately, to the best of the knowledge, as of yet, most of existing FPGA-based graph accelerators are typically designed for handling static graphs. In fact, real-world graphs are often subject to change over time, as known as dynamic graphs. For example, the Twitter user collectively sent 500 million tweets per day. Every minute, more than 100 hours of video is added to YouTube. More than 1 billion video viewed every day in the past year. To process a dynamic graph, it also relies on an iterative process with two basic kernels, graph updates and graph computation. Graph updates aims to generate a new graph by modifying a graph snapshot with edge and vertex insertion and deletion operation. Graph computation, which can be a graph algorithm or an ad hoc query, is then performed based on this new graph to extract useful information. Previous study shows that the graph updates can function as importantly as graph computation. An inefficient graph updates may lead to the unexpected outcome. An example is financial fraud detection, which aims to find fake transactions using the ring detection on evolving graphs. In this case, a slow rate update may cause the ring detection to operate upon an outdated graph such that the analyzed results can be inaccurate or even useless. Also, early studies on traditional architecture adopt novel graph representations like CSR variant, adjacent list, hash table, tree, packet memory array to improve the concurrent of dynamic graph updates. Their underlying efficiency is still limited due to the inflexibility of traditional memory subsystems. In this context, graph computation has been studied in existing FPGA-based graph accelerators meet dynamic graph very well, while graph updates is still understudied significantly. It is expected to develop a specialized FPGA-based graph updates library that can be easily integrated into any of the shelf static graph accelerators so as to support dynamic graph processing with minimum hardware engineering efforts. In this context, however, perform graph updates efficiency on FPGAs remains challenged. For a technical FPGA-based accelerator architecture, vertices are often stored in the on-chip VRAMs to reduce the random access overhead of vertex state. Also, edge has to be loaded into a streaming apply fashioned from the off-chip memory. In this context, a graph update operation can be split into three basic steps. Consider an edge update. First, the source vertex index of the to be updated edge is rated. Its associated edge array will be loaded from the off-chip memory and stored into the register attached to each process element known as PE. Second, the to be updated edge is then inserted into or deleted from the loaded edge array, which is finally written back to the off-chip memory. In the real world, there are often a large number of updates applied. The off-chip edge data may be repeatedly and redundantly accessed by each separate PE, thus resulting in expensive off-chip communication overheads. To demonstrate this paper conducted a set of experiments to break down the real computation time and off-chip communication time of graph updates operating over AQ graph. We see that the communication overheads dominate the overall execution time of the graph updates for all dynamic graphs. Therefore, the paper focuses on addressing whether and how the most off-chip communications arising in dynamic graphs update can be transformed into on-chip memory access. They observed that the dynamic graph updates operating upon real-world graph shows significantly special similarity for off-chip edge data access, in the sense that the most random off-chip memory requests come from accessing the edge associated with a few valuable vertex. Consider the realistic dynamic graph. Most, bigger than 99% of edge updates are associated with only 5% of vertex. Special similarity motivates us to classify the entire edge data into a high-value data if it is requested by many edge update and low-value data for otherwise case. There is a significant gap between FPGA on-chip memory and off-chip memory that cause problems into some applications. Fortunately, there is a new memory in the system design hierarchy called UltraRAM, which provides a much larger on-chip memory resource to fill that gap. Therefore, this motivates to reduce the most off-chip communications overheads by applying a differential data management in which for each batch of graph updates, high-value vertex edge are resident on the specialized on-chip UltraRAM, while most of low-value ones are stored in the off-chip memory. So on this side, the graph process GraSU, a fast graph update library for FPGA-based dynamic graph processing. The first contribution is a value measurement, which enables accurate estimations of the value of the vertex, while other value of wire memory management, which retains high-value data on-chip so that most off-chip data communications arising in graph updates can be transformed into fast on-chip memory. The first thing is to locate this frequently accessed data. A direct approach is to predict using the vertex degree. However, as shown in the right figure, the accuracy gap between the degree-based approach and the ideal case become bigger as update batch processed to make precise prediction. So quantify the value of a vertex as depends on not only its degree, but also its historical update frequency. Here in the equations, n is the number of the update batch and degree v is the number of outgoing edges of the vertex v. The if minus 1v represents the number of edge updates to the vertex v, also called the update frequency of v, in the I minus 1th update batch. The value of v is initialized to degree v before the 0th update batch starts. And also value to the power of I, v donates the value of v after applying I minus 1th update batch. Where this new approach is accurate, its overhead can be large. Fortunately, the interleaving between graph updates and graph computations offers the opportunity to hide the overhead. Based on the qualified vertex value, the next step is to naturally identify the high-value data that should be stored on chip. GraSU tries to store it as much large high-value data as possible on chip. Since the value and the edge number of each vertex are changed over time, and the on-chip memory capacity for different FPGAs is different, they must dynamically compute the high-value data, where the edge of V indicates the edge of V. Size S represents the total memory size of set S, and the absolute value V is the number of vertex. The V set is the set of vertex that has been sorted by their value from the largest to the smallest in the VMM module. And the absolute value of on-chip mem donates the on-chip memory capacity. This equation means to find the largest tau such that the total edge size of from V0 to V tau is nearly equals to the on-chip memory capacity. After tau is computed, we can then obtain the set of high-value data, here donated as the SHVD. In this different memory architecture, both Ultra-M's and the off-chip memory has the edge data. Thus, we must know which memory and where the corresponding edge data are located when a vertex is processing. A naive approach is to use another offset array to record the on-chip edge data, but it incurs extra space overhead, which can be more than n times 4b, where n is the number of vertex. So they represent a simple yet effective bitmap-based method to yield a good trade-off between space overhead and memory addressing efficiency. With the above design, the GraSU can efficiently handle dynamic graph updates. And other important things is to integrate the GraSU into an existing graph accelerators with minimum hardware engineering effort. As shown in the figure, they provided a uniform programming framework. Users only need to instantiate the accelerator module and then connect the accelerator's input and output signals with other GraSU modes for coordinating. For the evaluation, they integrate GraSU into AccuGraph to perform dynamic graph processing, reformed as AccuGraph-D running at Zheng U250 accelerator. They choose Aspen and Stingers as baseline and run them at a high-ended server. There are 3 graph algorithms: BFS, PageRank, and WCC to test on 5 real-world dynamic graphs. AccuGraph-D outperforms Stinger and Aspen by an average of 30 times speed ups and 4 times speed ups in terms of update through output. In addition, they improve further overall efficiency by 9 times speed up and 3 times on average. They finally explored to integrated GraSU into other 3 state-of-the-art FPGA-based graph accelerators, including FabGraph, Wave Scheduler, and ForGraph. Results shows that the dynamic graph version of FabGraph, Wave Scheduler, and ForGraph increase from GraSU also outperformed Aspen with geomean speedups of 3 times, and 1.63 times, showing the generality and the practicability of the GraSU. In conclusion, the paper introduced a graph structure update library called GraSU for high throughput update on FPGAs. GraSU can be easily integrated with any existing FPGA-based static graph accelerators with only a few lines of code modifications for handling dynamic graphs. GraSU features with 2 key designs, an incremental value measurement and a value-aware differential memory management. The former enables to quantify the data value accurately, while its overheads can be fully hidden before normal graphs computation. The latter exploits special similarity of the graph updates by retaining high-value data on chip, so that the off-chip data communications arising in date updates can be transformed into fast on-chip memory accesses. Also, the evaluation shows that the accurate graph D can run much faster than Stinger and Aspen. So here is the reference of these papers, and thanks all for listening. Is there any question?